Our next speaker is Thomas Porter about incremental bidirectional typing via order maintenance.
There we go. Yeah, I think it's on.
Perfect. And then if you don't mind actually taking off the...
Oh, how about this?
Oh, that might work.
Cool. Okay. Hi, I'm Thomas Porter, and I'm going to talk about incremental bidirectional typing via order maintenance. I'm at the Future of Programming Lab at the University of Michigan, and this is joint work with collaborators at the University of Utah. Okay, so first of all, this is very much a work in progress, and I'm as interested in hearing the advice of the experts in this room as I am in talking about my plan. So yeah, very much this is conveying a plan. And roughly in terms of how far we are, I made up these numbers, but we're most of the way through conceptualizing the plan, a chunk of the way into formalizing it in paper and in AGDA. A little bit of implementation work started, and we don't have anything to evaluate yet. Okay, but with that out of the way, our main goal is live programming. That's programming with continuous feedback of some kind. And people have talked a lot about what exactly this is, why it's desirable, how to achieve it. But today we're just going to focus on a concrete sub-goal, which is incremental type checking. And that is maintaining typing information while you're editing the program without having to retype check from scratch every time. So of course, people have thought a lot about this question. A lot of the prior work is in the implementation of language servers and compilers, incremental compilers. But a lot of that isn't necessarily written up or published anywhere. So one thing I'm particularly interested in is getting feedback from experts in this room about how that works. In terms of what has been published, of course, there's lots of work on general incremental computations or adaptive functional programming or self-adjusting computation, for example, by Mulcahy. In terms of type checking in particular, there's a line of papers about translating typing rules into data log programs to which you can apply a general incremental data log solver. Similarly, with a task engine, that when part of the program updates, you find which typing rules need to be reevaluated recursively. And of course, you can memoize calls to functions or type checking functions with unchanged inputs. There's also related work with respect to incrementalized browser layout computations from Utah with our collaborators that uses some of the techniques that I'll be talking about today. Okay, first of all, our particular setting, we're going to think about structural edits. So if you went to the syntax and editing session at Pavel on Thursday, you'll have heard about this. But basically, we're considering changes to the abstract syntax tree of the program directly in terms of like a graph edit, a graph rewrite, hopefully local in some sense. So for example, here we have a bit of an AST for simply typed lambda calculus. The int is like a type annotation for the argument, and ask means ascription, so it's like a node representing E has type tau. And it would look in concrete syntax like you see on the left there. And a structural edit might look like this. So if you wrap this subterm in an application node, function application, it would go like this. So the binary function application then needs an argument, and we might fill that in with an expression hole leaf node. And we're interested in this partially because at Michigan, we're working on this structure editor, Hazel. But also, we can consider this just to be a convenient interface to our incremental typing theory. You can imagine using it in a different context as long as you translate, say, your text edit actions into structural edit actions. OK, also expanding on our setting, we have some non-assumptions. So we're not explicitly modeling cursor movement. We're not assuming that edits take place some amount of time apart or some distance of space together. And the main reason we're doing that is so we can model collaborative editing, hopefully. And there was a talk earlier in the week about collaborative structure editing that this should be able to interface with. But don't worry about concurrency or commutativity or any of those concerns here. We can assume that the edit actions are linearized. We also don't assume restrictions on the program structure in terms of we don't assume the existence of files or modules or even top-level definitions. We just have one AST with all nodes treated equally, which means our incrementality has to be at the fine-grained level of AST nodes. And we don't assume a particular bound on the program size. So to elaborate on that last point, we're guided by this kind of very aspirational vision of live, massively collaborative programming. So if we imagine that there's one giant program, say the size of Wikipedia, that everyone in the world can be editing at the same time collaboratively, also like Wikipedia. And in this setting, certain approaches like retype checking the subtree rooted at an edit just won't work because that can be arbitrarily large and in fact arbitrarily wasteful because an edit that's near the top of the tree might not actually require much retype checking. Say if you make a let binding but don't actually instantiate the variable yet, you don't have to delve into the body. What we want is something more like, this is kind of abstract and I'll make it more concrete later, but working outwards from the site of the edit action and only updating exactly what needs to be updated kind of in a local way. OK. So first of all, this is about incrementalizing something. What exactly are we incrementalizing? What's our type system? Well, a year ago at Pavel 24, there was this paper on total type error localization from the Future of Programming Lab. And it introduced a formal system called the marked lambda calculus, which I will try to briefly summarize. So for example, here's one of the typing rules. And I'll break it down a little. So the first thing to notice is that it is a bidirectionally typed system, which fortunately has been discussed, I think, twice already today in this workshop. But the feature of that we'll use is that information flows locally through the AST, kind of up and down the edges in the AST. Another thing to notice is that it's not just types that are being analyzed here, but this judgment kind of takes one AST and inserts these red marks, the hot dog buttons there. And those are kind of localized type errors. And because of that, in this case, that error is because this is a function application node, but the left-hand side is not a function type, as you see in the premise. And if we want to keep type checking in the presence of these localized error marks, we need to give them a type. And so we use the dynamic type from gradual typing. OK, so those are some design choices. And the main advantage they give us is summarized in this theorem, which you don't have to read. But basically, it's totality. It's that this is a total function, and that any syntactically well-formed AST can be marked in this way, just by inserting these localized type errors in a way that respects the static semantics as defined in the paper. OK, so there's an obvious way to turn that judgment into kind of an editor, which is if we start with a bare AST, E1, we can mark it, insert the marks, the local errors, into eCheck1, and then display that to the user. They can see where their errors are. And then the user can apply an action alpha to the bare AST E1, making a new AST, which can then be remarked, redisplayed ad infinitum. But the problem is when these marking stages get expensive. So naively, to remark the program, you have to traverse the entire thing linear time, and that's not going to scale as we take kind of the infinite size limit of the program. So this is exactly the kind of diagram that you're looking at when you decide to try and incrementalize something. Is there a way to go directly or more directly from eCheck1 to eCheck2? And our approach is to apply the action to eCheck1 in some modified form. And we don't directly get eCheck2, but we get something that can then step to eCheck2 according to our small step update propagation dynamics, is what we call it. So we have these two judgment forms, one that applies an action to this kind of marked up annotated program, eCheck, and one that can step these annotated programs, which kind of propagates the actions, the updates outwards from the action, and which I'll talk more about later. Okay, so why do we do this? Well, one advantage is just conceptual. It kind of like lines up with the existing type system in a nice way. But also it has the practical advantage that, say we're in this case where we have a program, you apply an action, and then there's lots and lots of steps that need to happen. There's lots of updates that need to be propagated. And even in the best case, even in the most incremental case, one edit might incur arbitrarily many marks that need to be inserted. So say if you change the type of a variable that's at the top, then everywhere it's used might become a type error, and you need to take at least n steps if you change n marks. And during that time, we don't want to lock the editor for you or for your collaborators. And so by giving it the small step dynamics, you can actually jump in and keep making edits while these updates are being propagated. And we think we'll be able to prove a theorem that no matter how you interleave these actions and these update propagations, the result will always be the same. It'll always converge, and it'll always agree with what you would have gotten if you had retype checked from scratch. Okay, so that's all very abstract, but now I can show you what it actually looks like on a program. So here's an AST in our simply typed lambda calculus. We also have some additional data. So on the edges, you can see the synthesized types, the up arrow, that's the inferred type at the subexpression, or the analyzed types, the down arrow, the expected type at that subexpression, or both. And we also see some marks, some localized errors. So at the x variable leaves, we find an expected bool and an inferred int. And since those don't match, we have this little red slash mark, which represents a type error, a mismatch. And we could also have errors at other locations, but we won't see that in these examples. So I'm just going to step through what these two judgments look like, applying an action and propagating the updates outwards. So say the user edits this Boolean in the surface syntax directly with an action into an int. They change it. And that's the whole action application judgment. It's it's O of 1. And we get this state. And the int has a star. And the star we can think of as a to-do for the update propagator. We can think of it as the frontier of propagation. It means it's new, but its ramifications, direct ramifications, have not been computed yet. So in this case, it's within a type. It'll just bubble up. This arrow type is new. And then we hit the ascription. And again, the left branch of the ascription is an expression. The right branch is the type that the programmer asserts this expression has. So now I'm going to show some formalism. This is the inference rule that's used to step in this particular case. It's an ascription with a new type. The ascribed type is new. And actually, let me explain the syntax a bit. Hopefully you can see that. So the important thing here is that the E expression sort has all the normal constructors, and it has locations for every possible mark or type error. But it's defined in terms of eCheck, mutually recursively. And eCheck has an E, an expression, and S, which is synthesis data, which is optionally synthesizing a type, and the type optionally is marked as new. And then it has a location for a mark to be, an error if the synthesized type doesn't match the analyzed type, and then it has an analysis data, which is like synthesized data. Okay, so that's just an explanation of the syntax. And now we can apply this rule, and we see that the ascribed type is no longer new because it has been propagated to the expected type under the ascription, the synthesized type above the ascription. Okay, and so now we can see where this update propagation dynamics is non-deterministic. We have two to-dos, 2 points on the frontier, and we could choose to propagate from either. But for the sake of example, let's take the lower one. We're analyzing a type against the lambda with a new expected output type, and that translates simply to a new expected type for the body of the lambda. And now our data flow path has kind of reached the end. There's a mark here because the old Boolean didn't match int, but now the rule, as shown here, says if you're at a variable and you have a new analyzed type, what you should do is think again whether these types match and update the mark accordingly, and then we're done. And indeed, they do match, and we change that type, and the user would be able to see that, and then that bit of the frontier is gone. And now I can demonstrate the interleaving of update propagation and actions. So before we propagate this to do in the middle of the screen, let's say the user changes this int to a Boolean instead. So this one's quite interesting. So this means lambda x of type bool, and then the body. And so two things need to change when you change the annotated type on lambda. One is that the inferred type of the lambda changes. The input type is now bool, not int. But also, the inferred type of all the x's that are bound by the lambda in the body need to change. So let's just assume for now that there are pointers directly between each binding site. Sorry, those should be attached to the lambda, not the bool, to the bound variables. And we'll return to the question of how to actually maintain those pointers throughout structural edit actions. But we can assume that we can go directly from the lambda to the variables, and this is what happens. So yeah, the found type at the top of the program has changed, and the inferred type at each variable x has changed. And now we can just step through some more. So the bottom x, we reevaluate the consistency, whether the types match, they don't match anymore. And then up here, now they do match. And then we can return to our star in the middle. There's a new output type for the function that's being applied. So it's a new found type for the application. And then that's a new type for the body of the lambda. So it's a new output type for the lambda. And then we're done with this subtree. And if this were part of a larger program, we could continue to propagate. And if this is the root of the program, then the star, the frontier, kind of fizzles out, and we're done. OK, so that is a description of the local part of the scheme that kind of implements the bidirectional flow. And the only tricky part left is the context, the non-local part. So we are confronted with a problem when maintaining these binders between maintaining these pointers between bindings and bound variables. And that is, say we insert a variable x. We have to know whether it's in the scope of, or which binder it's in the scope of. And that's kind of a non-local computation. And the obvious way to do that would be to walk the spine of the tree. You start at the x, you walk up, first lambda x you find, that's what binds it, or you hit the root. But we can't assume that the program is a balanced tree, and that could be O of n in general. So we want to do better than that. So yeah, it's hard to distinguish between these two cases without doing some heavy non-local computations. So one idea for at least checking ancestry is, say we had on each AST node an interval of numbers, such that containment of intervals corresponds to the ancestry relation in the AST. So in this case, lambda x is an ancestor of x because the range 0 to 11 contains the range 8 to 9. And then we can check ancestry efficiently by just comparing these four numbers. So that's an idea, but it raises more questions than it answers, actually. So first of all, we don't just need to check ancestry. We need to find the lowest ancestor of x of a certain form. So our plan to do that is, say we're just thinking about x, we can treat each variable independently. Every lambda x, or every binder for x in the program, we're going to put in a balanced binary search tree. And the nodes in this BST include the left endpoint of the interval and the right endpoint, and also a third number, which is the max of the right endpoints in that subtree of the BST. So here at the root, that third number is 7, because 7 is the greatest right endpoint contained in this tree. And the BST is sorted by the left endpoint. So then, just stepping through an example, say we insert an x here, and its interval is 5 to 6. So we'll start at the root of the BST and check whether x could potentially be found here by using an over-approximation of the interval. So we're not going from 1 to 4, we're going from 1 to 7. And indeed it could. And in that case, we're going to recurse right. And the reason we recurse right is because the right branch has the highest of the left endpoints, because it's sorted by left endpoint. And higher left endpoint means lower down in the tree, so better candidates. We want the tightest binder. And then we do the same check, and we find that 5 to 6 is not in the range 2 to 3, so we reject the subtree, pop back out, and now we check the direct interval found in this node, which is 1 to 4. Again, 5 to 6 is not in 1 to 4, so we're forced to recurse left. And in this case, we do find that 0 to 7 contains 5 to 6, and so we return this binding location, which is in fact the tightest binder for X in this tree. Okay, so that's one problem. But there's another problem, which is how do we actually come up with these intervals? And how do we maintain them while editing? And for that, we're going to have to go back in time to the 80s. There's this paper, 2 algorithms for maintaining order in a list, that lays out an efficient implementation of the order maintenance data structure. And I won't talk about the implementation, but I will talk about the data structure and its interface. So an order maintenance data structure has a totally ordered set of elements, and it supports the following operations. You can insert after a given element. That'll return the new element and mutate the data structure to insert it. You can delete a given element, which again mutates. And given 2 elements, you can just purely check their order in the total, their relative order. And the key thing is that all of these operations can be made logarithmic in the size and the number of elements. So how do we exploit that? So if we go back to our original structure editing example, say we want to wrap this subtree headed with the ascription in an application, like so. Well, we can take the right endpoint of that subtree and insert 4 new elements afterwards. And yes, we're using the elements of the data structure as the endpoints of the interval. And then we can take those 4 new elements and put them in as the endpoints of our new nodes in a way that preserves our property of containment. I think there might be a bug there. Sorry. But yeah, and with generalizations, we think we can apply this to other structural edit actions like deleting and moving using generalizations of the order maintenance data structure that work on batches of elements, not just single elements. Okay, so that is pretty much our plan. And now I hope we have time to talk about some of our open questions and hear from everyone here. So one open question is, how is incremental type checking approached in practical systems? And we also have a kind of technical puzzle about prioritizing the updates. So it's a non-deterministic propagation. I don't know what that thumping is. It stopped. Okay. So yeah, we have multiple choices of which stars, which to-dos to propagate next. But it's much better to choose some orders than others. So if you have an upstream frontier and a downstream frontier, you want to do the upstream one first, because once it catches up to the downstream one, then you only have to do the downstream stuff once. Whereas if you do the downstream stuff, you might have to do it multiple times as different waves catch up to it. The problem is that it's not clear what the upstream order actually is, because it doesn't correspond to the AST order. Yeah.
Oh. Yeah. The gym is on this floor. So I guess let's just ignore it.
Yeah, okay. So yeah, that's like kind of a technical question that I'm not sure about. Is it possible to achieve greater incrementality? So if we imagine a case where someone keeps editing a type in the surface syntax, but without changing the expression layout, that might continue to affect, say, the presence of a type error somewhere else. But as specified here, that type would have to traverse the AST in basically the same path every time that it's changed. Is there a way to potentially remember that path and skip to the end unless the path itself changes? it seems like potentially there's room for improvement there. And related to that, can we actually use one of the generalized approaches that we discussed at the beginning to achieve a system with the same desirable properties that this one has, namely at least as incremental, and hopefully with this ability to interleave actions and updates. And that one is pretty critical because as the size goes to infinity, then the wait time might have to go to infinity to see the effects of your actions, and you don't want to lock the editor while that's happening. But there are difficulties with kind of direct incrementalization of the process because, first of all, the information flow in the bidirectional setting is kind of nonlinear. It's not just a fold over the tree. And information through the context, it's kind of hard to tell the fine-grained data flow there. You don't want to confuse, propagation through the context of one variable with another and waste time there. So yeah, I'd love to hear your thoughts on that, and I think we have plenty of time for that as well. But thanks for listening.
Questions?
Thanks for the great talk. This is really interesting. We've used order maintenance data structures or tried to use order maintenance data structures for a totally different purpose in a type system before. It didn't end up working, but we should talk more offline about that. The actual question I have is, at one point when motivating this description of the problem where for which you need these BSTs of sort of all the same variables, you described sort of at the time when the user inserts the variable, when they do the edit update action, right, like right there, where you put in the X, how do you know that it's the 56X as opposed to any other numbers of X, right? Presumably the user has typed an identifier name like X. And so this may be a really dumb question, but like, why do you know which level of you're trying to find the 5 and the 6. That's not given to you at that point, right?
That's not a dumb question, but in the model we're thinking of, you're inserting an X at an expression hole already. So you already have like a question mark node with an interval that exists, and then it just uses the same one.
Could you explain how this BST is ordered again? I didn't really understand this bit of the presentation.
Yeah, sure. It's sorted by the left endpoint.
By the left endpoint.
0,
Okay.
1, 2.
Mm-hmm. I see.
That's and that's the sorting order, and then the third number is the max of the right endpoints in the subtree of the BST.
Yeah. Okay, I think I just have to look at this slide a lot offline to understand it.
Yeah, sure.
If anybody else has other questions.
Hi, really nice talk. And I wonder if we could achieve that. For example, if we have a real large type, so if we edit only a part of the type, say the bool, can you switch to the type AST slide? Yeah. So for example, instead of not instead of. So for example, the bool on the right-hand side of the arrow is really large. And we modify the right-hand side, or we modify the return type of. So do we need to check that the left-hand side, which is really large, to be the same as the type is propagated, or we could probably propagate the change only on the right-hand side part?
Yeah, that's a great question, and we've thought about that. So maybe we could just use Merkle trees. To try and achieve like roughly constant time structural comparison. And then if you find that the thing didn't change elsewhere in the flow, you just don't continue, like the star fizzles out. But we also had this system where each type tree was accompanied with like a newness tree, which kind of mirrors the structure of the type up to some point and marks different subtrees as either new or old. And then you can, while you're like wrapping and unwrapping these trees, you can efficiently figure out whether something never changed at all. But I'm not sure that like we've completely solved that part of the problem, but that is an important consideration. Yeah.
Okay, I see. Thank you.
Mm-hmm.
Thank you for the nice talk. I guess this system, this ASD-based system, error propagation system seems like it can be applied to some error fixing, error recovering system. Do you have any thoughts on that?
I guess I'm not really familiar enough with such systems to be able to comment on that. But I'd like to hear about it offline if you want to talk about it. Yeah.
The questions?
I seem to recall order maintenance is used in self-adjusting computation. Is it used in a similar way, or is this just a curious coincidence?
So as far as I understand, it's used mainly to address the second point here about prioritizing the updates. Like it maintains what is upstream of what. And when we tried to make an analogous system here, what counts as upstream in the bidirectional flow is just too unrelated to the AST, and it can switch in these non-obvious ways so that we can really figure out how to make it line up with an order maintenance structure. But I think that's how it's used. And I think the scope usage, which by the way is also used in the browser layout computations, I think it's kind of a coincidence as far as I know that they're both applicable.
Cool.
Mm-hmm.
So the vision of a Wikipedia-sized program, that is mind-bending to me. I mean, I think of an AST of some immutable data type owned by a single thread. How should I even think of that at that size? Is it some mutable data structure in a single process? Are we already talking about the compiler as a distributed program?
I'm picturing distributed, yeah, but I don't know how the details would work out. I'm picturing it distributed, and like maybe we could have like message passing along like boundaries in the giant AST. Yeah, I mean, Cyrus has also thought about it if you want to chime in.
Yeah, makes sense. I mean, I guess it has to be at least that, yeah.
You want to comment on the mutable versus immutable representation?
Well, like with the structure sharing. Yeah, so one thing we thought about is this appears to store copies of the types at every edge in the AST, which would naively be really big. And so we think that like structure sharing within the types, but with mutable expression trees could be a good compromise here. But then that kind of breaks the distributed picture, I think. So I'm kind of picturing like boundaries between subsystems, and within each subsystem or each like process or whatever, then there's structural sharing, but then there is duplication across these distributed subsystems.
Okay, let's thank the speaker again.